All right, it's streaming. Audio is good. Some people in my cisp310 class, told me that the audio is choppy sometimes. So have you guys experienced, the audio being choppy?
Like 205.
Tiny bit? Okay. But it's not too much that you cannot understand the audio portion. 30%? Well, that's pretty
Depends what
bad.
area. Sometimes it gets really bad in like one section of the
Huh.
video.
I have to find out why, because,
Microphones are turning and it's rubbing against the microphone.
oh, okay,
It's
the
more like it
scratching
cuts
sound?
out instead of
Yeah, or
like
It
it
cuts
sounds
out
like
like completely?
it more so cuts out or like it
Huh.
starts cutting out.
Okay. Well, do you have to kind of point to the no phone, food, and drink, sign, so, because I don't want to be, asked to help clean up this classroom by the people who usually would clean up the classroom. All right, so we'll go ahead and get started. This is your new lab for today. It is a little bit long. It's worth a little bit more points. Okay, so we'll kind of go through a preview, and then we'll go back and talk about the material that you will need in order to do this lab. So this is the first quote-unquote question. I don't think it's actually a question. It's just telling you the convention between the caller and the callee. Remember what we're doing right now is to talk about the convention between the caller and the subroutine being called. They have to agree on many things. So the first one is parameters are pushed on stack before the return address. Okay, so that's one of the things that is done. Okay, and then within the parameters, if you have more, the last parameter is pushed first. Okay, that's a bad grammar there. Local variables are the responsibilities of the called subroutine. We'll talk about local variables today. Register D is the stack pointer. We have talked about that quite a few times already. Register A is used to return scalar values. So that means it is only used, okay? It's only meaningful when you have a subroutine that returns an int, a pointer, a char, or something like that. But if you have a void function or a function that returns void, then register A is not special in any way. Register B and C can be modified by a called subroutine without restoring their original value. In other words, from the caller's perspective, you cannot assume register B or C to retain its value. Yes?
Sorry, is the microphone on?
Oh, this one is not. Now it's on. There you go. Thank you. So the flag register can be modified by a called subroutine. So once again, register B, C, and the flag register, the caller cannot count on those particular registers to retain the value across a subroutine call. Which also means if register B is special to the caller needs to save it before the subroutine call so that that value can be restored later on. A called subroutine is responsible to deallocate the return address of an invocation, so that we have used quite a bit already in the previous lab. A caller is responsible to deallocate stack space used by parameters. So that's a split. So the arguments is strictly the responsibility of the caller. The return address is kind of split because the caller is going to push the return address, but it's the called subroutine to deallocate the return address. So that one is a little bit tricky. Okay, so this slide is really just a list of things that we have talked about already. So this convention is important because it tells us how a caller and a callee would communicate. Furthermore, it also allows us to make certain assumptions and also to understand applicable constraints. Okay, this is the first question. Okay, the following C code needs to be implemented in this program. Are there any global variables? So that has nothing to do with assembly language programming whatsoever. It's just the identification of local variables versus global variables. This one talks about a local variable is by default auto. Is that concept discussed in cisp360 that local variables can come in two varieties? One is auto and the other one is static. Was that ever discussed? Yeah, you usually don't say auto because that's the default. But if you want it to be static, you have to use the word static. So this means they're stack-based, which also means every invocation gets its own local variables. So does everybody understand the difference when I say the invocation of a subroutine versus a subroutine itself? Okay, so an invocation is a runtime thing, and the subroutine definition is a compile time thing. This means that if the variable only takes up space during the invocation of the subroutine that's containing the variable, the local variable, consider the following C code. So in this case, local variables x and y do not even exist until the subroutine is called. So let's just kind of stop here, and we'll go ahead and implement this particular useless subroutine. Now, it is quite obvious this subroutine is completely useless, right? Because what does it do to the caller? Absolutely nothing, right? But does it hurt anything? No. Would it corrupt anything? No. It's just being useless to the caller. So let's go ahead and implement this particular subroutine. It's actually also listed here, which is one way to implement that particular subroutine. But we'll go ahead and implement it here. I'll just use Notepad on the side. Okay, I'll pick one of those and just restart it from here. Okay, there we go. All right. So with this particular subroutine, I don't have to worry about parameters because as you can see in the C code, it doesn't take on any parameters. It has no return values either. So the main point of this particular subroutine is really just say, okay, how do we implement local variables? So the first thing we do is we just say f, okay, which is the entry point of the subroutine. So that part has not changed. Then the next few things we're going to do, well, I'm going to deviate from the example in this particular description, okay, because I want to give you some different exposure of how things can be done, so that when you look at each way of doing things, which are quote unquote equivalent, you can understand that they actually get the same thing done, even though they are slightly different when it comes to the approach. Okay, so what we want to do is to have a picture of what the stack should look like. Okay. So the stack would look like this, okay? At this point, right at the entry point of the subroutine, the only one thing you can rely on is the return address on the stack. And we also know that we can assume register D, which is our stack pointer, is pointing to the return address on the stack right now at this point. Is that okay? All right. So now the question is, well, then what do we do to deal with the two additional local variables that we're supposed to have in this particular subroutine? We have local variable x and we have local variable y. They're also supposed to be living on the stack. So to do that, we have to decrement the stack pointer. Okay, so what we do, the first thing we do is decrement D. Okay, so now what does the stack look like? Well, it still has the return address on the stack, but now it also has the first local variable on the stack. Now, which one do you want to be the first one to allocate? It doesn't really matter, okay? So the compiler actually has a choice of whether x should be the one that has a higher address or whether y should be the one that has a higher address. Now, most compilers compile from left to right, and it will do the allocation according to that order as well. So according to that order, x is going to be the one that has a high address because it is allocated first. So in that case, we have x being our local variable. And at this point, the stack pointer is now pointing to x, right after the decrement D instruction. Is that okay? Okay. And then we have another decrement instruction. Okay. So this time, the stack would look like this. We still have the return address on the stack. We have x on the stack. And now we also have y on the stack. The stack pointer is now pointing to y. Are we doing okay so far? Then you might want to ask, what are the values of x and y? Because we just allocated the space, but we did not initialize those locations. The answer is we don't know. We really do not know what the values of x and y are at this point, because we just basically say, well, whatever this byte is, it is now x. Whatever this byte is, it is now y. But we did not initialize those locations. So those locations on the stack would still have the values from before. So x and y has values, but we do not know exactly what those values are. Are we good so far? Okay. So now I'm going to use a convention that is not described in this particular slide, but I'm going to do it like this. Okay, I'm going to say x as a label. We'll define x to be, well, we'll define y first. Okay, so we'll define y to be 0. The reason why I define y as a label to be 0 is because y is representing, y the symbol is representing the number of bytes that is between local variable y and where the stack pointer is pointing at. And that's why it is given a definition of 0. So I'm going to write it down here. Okay, so offset to local variable y is 0 from where the stack pointer points to. So does it matter, this is called from main or it's called from another subroutine or is recursive even? Nope, does not matter at all because it is only relative to this particular invocation, y is 0 byte away from where the stack pointer points to. The next thing I'm going to do is to do it like this, okay? And you guys some of you would go like, what is that? Remember, in the expressions in the TTP ASM assembler, we can only use postfix notation. So in postfix notation, this is basically saying 1 plus y, or the sum of y and 1. Well, you go like, but we could just say 1. I mean, that's the same thing. It really is the same thing. But this really shows the relationship between x and y. X is 1 byte above y. That's all it's trying to say. Okay, so as a symbol, x is just 1. I mean, every time we see the symbol x, the assembler just says, oh, you mean 1. That's exactly what the label is doing. But what is it representing? It's representing that the offset to, oh, okay, typo here. So that's supposed to be a 2, not a FO. So there we go. So the offset to local variable x is 1 byte from where the stack pointer points to. Okay, I see that the part of the screen is cut off, so I'm gonna look at that. Okay, and I can just kind of do it like this. There we go. So now I can say about the same thing. I can say offset to local variable x is 1 byte or 1 location from where the stack pointer points to. Is that okay? So if you want to, you can even do the return address. So you can say return address is x1 plus. So what that means is offset to the return address on the stack is 2 from where the stack pointer points. Is that okay? Yep.
So basically, variables are label definitions of the location.
You can use label definitions for anything you want. But in this context, I am using x, y, and return address as labels so that I have a symbolic name to refer to things that are on the stack. And the symbolic name is telling us how far those things are away from where the stack pointer points to.
And is this the standard for every function?
It's up to you. So the point is I need to access my local variables. So there are a few ways to do it. So one way to do it is just to play around with register C or another register, make a copy of the stack pointer to another register and then move it around. But this is another way to do it. So I'll show you how we actually make use of it. Okay. All right. So are we okay so far? Basically y is just 0, x is 1, and return address is 2 as far as the label definitions are concerned. Okay. Now, that does not say anything about the values of the local variable x and y, nor the return address that we're supposed to go back to. This is only telling us where to find x, y, and the return address. If I know where the stack pointer is, I can now find x, y, and the return address. That's all these labels are designed for. Yep.
Those are the locations on the stack where we're setting them to.
They're on the stack.
Do we know specifically where, or are they just?
We do not care, because the assumption is at the entry point of the subroutine, the stack pointer points to the return address. So if I can use that assumption and then I do 2 decrement D instructions, I would have allocated the 2 bytes, 1 for x and 1 for y. I just need a label so that I can go back to where they are. Yep.
When we have needed a address as a variable though?
Nope, because the return address was pushed by the caller. It was there to begin with.
That makes sense.
Yeah, because remember when we push, the stack pointer goes lower and lower. So the return address was already there at the entry point of f, but the to decrement instruction would also allocate the space for x and y, having the stack pointer to point to y right after the to decrement d instructions. Yep.
So we've pointed to X and Y, but X and Y don't actually mean anything right now, though.
So they're allocated, but we have not used those locations yet.
That wasn't done by the caller. It's going to be done by the callee.
Correct. So the callee, because the callee is the only one that knows how much space is needed for local variables. The caller would never know that. Okay. So now we can do some work with these. Okay. So we want to do the first statement, which is x gets a value of 5. Okay. 5 is easy. Okay. We just do LDI A5. Okay. So this is the right hand side of x equals 5. Pretty easy. So whenever you have an assignment operator, whatever is to the left-hand side of the assignment operator is called, well, not very, creatively called the left-hand side, okay? But the left-hand side is special in a way because whatever is on the left-hand side needs to have what we call an L value. The L value is really just the location, where are we supposed to store something? Because the assignment operator, what is the job of an assignment operator? To assign, which basically boils down to the change of some memory location, right? So to change the memory location somewhere, you need to know where we're supposed to change. That where, has a technical term called the L value, okay? And you might think that I'm kidding you. No, I'm not kidding you. It is actually called the L value, okay? So now we need to compute the L value in this case, which is the address of x. So how do we get to the address of x? In other words, we need to get to this location, okay? We need to get to the address of this location. So now that we have symbolic names, it is a lot easier because I don't need to mentally keep track of, oh, x is the one that is 1 byte on top of y or anything like that. Because now I can just use the symbolic name. I say LDI, we'll use register B for this purpose, okay? So at this point, B is, guess what? Not much. It's just 1, okay? Which is not exactly what we needed. But we can do something like this now. Now this is the magic. At this point, B becomes the address of x. Let's see if we understand how this works. Okay? Does everybody understand how line 16 and 17 together is loading the address of x into register B? Yep.
So register D has the address of the stack pointer, which is some,
No, register D is the stack pointer.
but it's holding an address.
It's holding the address of local variable y.
So when you add 1 to it, it pushes up 1 byte to,
It moves the pointer up to the address of x.
but you're putting that in register B and leaving register D unchanged.
That is correct. You don't want to mess around with register D, okay? So don't do all the stack calculations using register D. So we'll get to the reason why that is the case in just a little bit, okay? But is that okay? Does everybody understand why on line 17, when it's done, register B ends up with the value of, ends up with the address of local variable x? Yes?
So D is the stack pointer, and when it's loaded into register B,
It's not loaded into register B. It was added to register B.
then, and how does it get the value of X again?
Because of how the stack is arranged, the stack pointer points to local variable y. X is 1 byte on top of that. So if you add 1 to the address of y, you get to the address of x. Yep.
How do you keep track of, if, let's say you have like a ton of lines, a lot of lines of code, how do you keep track of where the pointer D is at and where you need to point it at?
D is always the stack pointer. So you kind of know where D is supposed to be all the time. The only time it's tricky to know where D is pointing to is when you're already working with pushing parameters on the stack. then D does move away from where it is supposed to. It would no longer be pointing at Y. So that's the only time when it's a little bit tricky. But other than that, okay, the stack pointer should always point to kind of the same place. Are we okay with that? Okay. So now that we have the address of local variable X, we have the right-hand side value, we can just now do a store. So the store to B with A would implement exactly X equals 5 in this case. Because the dereference of B is basically doing something like this, right? Who is the address of X? Who contains the address of X? B does. So by dereferencing register B, I'm actually now storing to where register B is pointing to. But where was register B pointing to? Local variable X. So that's why this statement by line 18, we would have stored the constant of 5 into local variable X. Okay. So the next few lines, to store 20 into Y would be about the same. LDI A20, LDI B again, with Y, and then we do add BD. So don't forget the add BD because that is really important. And then we do a store to register BA, and that will eventually, basically get this done. So when this is all done, we just have to return to the caller. And to return to the caller, we do a LD instruction to retrieve the return address. And throughout all this, yes?
In this case, Lou, don't you have Y set as 0, meaning you're not adding anything to the stack pointer when you do the add BD?
You're absolutely correct. Y is actually just 0, so I could have just said, store DA. That would have done exactly the same thing, but I didn't do it for a reason, okay? Because if you want to add additional local variables, everything would get shifted around a little bit, right? So there's no guarantee that Y as a label stays as 0. So if Y does not stay as 0, I don't want to make a special case and say, well, since Y is 0, I'm going to use this approach, but since X is not 0, we'll use the other approach. I want one consistent approach to access all the local variables as well as the parameters, and this way works out pretty universally. So yes, it is kind of a waste of instructions in this particular case, but from the other perspective of what is the consistent way of accessing something that is either a local variable or a parameter, this is so much more reliable compared to, well, let me keep track of register C and where it's pointing to. So now we can just go ahead and do the return. So we retrieve the return address from where D is pointing to, because D stays the same the entire time, okay? From the entry point of the subroutine, well, actually from the time we allocate for the local variables, all the way to here, D has never changed. But I just pointed out one thing. I have to correct myself, because before we get there, okay, we have to increment D twice before we get to this one, because otherwise we'll be retrieving local variable Y as if it is the return address, and that would be disastrous. Okay, so we have to increment D twice on line 25 and line 26 to deallocate the local variables. The first one would deallocate local variable Y. The second one would deallocate local variable X. So after those two, the stack pointer would once again be pointing at the return address. And then just give me a second here. Then we can do the usual return sequence. Yes, go ahead.
Is there a way to do that part dynamically if, say, maybe you don't know how many local variables to allocate beforehand?
That gets a little bit complicated, okay? So if you do not know ahead of time how many local variables you have, then you can still continue to do the allocation kind of dynamically, but the displacement would continue to change. So as soon as you encounter more local variables, like in curly braces, you can define additional local variables. So that would change the offset to the ones that you have already allocated earlier. Do you see what I mean? So it's usually a better idea to know ahead of time, how many local variables you need, or how much space you need, and where you want to put each local variable. and just have everything statically determined at the entry point of the subroutine. So this particular way does not handle local variables defined within a certain scope very well. But that usually is considered a compiler trick instead of a, so the compiler probably did all the allocations in one shot. It's just the scope control tells you in what scope in the code you can access which local variable by what name. So we're not going to deal with that complexity in this class. Yep.
I kind of remember reading about interrupts,
Mm-hmm.
and so how would you, when can an interrupt come in, and how would that mess with this?
Very good. Okay. So I'll put this one on one side, and then I'll give you another version, which is not going to work. Okay. So we'll copy and use another mouse pad. So Control or Control Paste. There we go. Okay, so we're gonna work on this one. It is not, the code is not gonna work, and then I'll explain why it is not gonna work. So in here, okay, instead of, when I try to access, X, okay, so instead of doing this, let me present another way, quote unquote, another way to do this, but it wouldn't work. So I can increment D and then store A to whatever D points to. It seems to be doing the same thing. I mean, they're just far less instructions here. And then with this one, we just have to increment D again. So we replace these two with increment D, and then we can now store A to D, because at that point D should also point back to local variable Y. But this is not going to work in general. Okay, with a toy processor it would still work, but I would count it as an incorrect answer because in general it's not going to work. The problem with this code has to do with this. Whenever you change the stack pointer, whenever you increment or increase the stack pointer, you have to be sure that whatever it is currently pointing to is no longer needed because it can be gone. Then go like, how? I mean, this code here does not actually do any changes to whatever the stack pointer points to until we actually get to it. So what do we mean by something can be changed? So this requires a whole kind of slightly different discussion of interrupts. I think I have not talked about interrupts in this class because you guys are one class behind the Tuesday, Thursday one. So the concept, yeah.
I think you covered it briefly last.
I covered it very briefly. Yep.
You told us they exist.
It exists. Okay. So the idea of interrupts, so there are two ways to interact with input-output devices. So input devices, are, okay, so the cell phone actually is much better for this demonstration. So on a cell phone, the accelerometer is an input-output device. Your touch screen is an input-output device. The buttons are input-output devices. The microphone is an input-output device. The screen itself is an output device, but we are more concerned about input devices instead of output devices. Okay, the Wi-Fi chipset is an input-output device. The Bluetooth chipset is an input-output device. The USB chipset is an input-output device. So I think you got a general idea of what an input-output device is, or what an I/O device is. So now the question is, okay, you can see my screen is now blank. If I shake it, I get it to display what they call either the screensaver or one of the screens that it will display when it thinks you're trying to access it, right? Okay. So now the question is, how does it know? How does Android, the operating system, know that I'm shaking the phone and it's time to display the clock and whether I got messages or not? Okay. So there are two general approaches. One is called polling. The other one is called interrupt-driven. Polling is easy. Okay, polling means the operating system, Android in this case, is constantly asking the accelerometer, okay, and say, did you experience any change of force that is exceeding this particular threshold? Okay, as soon as it got the answer from the accelerometer, it would ask again. So it's basically asking the accelerometer like millions of times per second. Okay, but during that time, it's kind of difficult to ask other devices, right? because it also has to ask the Bluetooth chipset and say, well, did anything try to communicate to you using Bluetooth? And it has to talk to the Wi-Fi chipset, right? Did you receive any packet through the Wi-Fi, chipset? It also has to talk to the 4G chipset and say, did you receive anything from the cellular, communication part? So polling doesn't work very well unless there's only one thing you need to poll. Two, polling is also bad in this particular case because it would just chew up my battery life. Because polling is continuous, which means the processor is busy all the time asking that dumb question over and over again, millions of times per second. And as a result, the processor never really get a chance to quote unquote rest or get into a state where power consumption is all the way down. Is that okay? So instead of using polling, we use an approach called interrupt driven. So interrupt driven means when the processor has nothing to do, it just goes to sleep. It just dozes off, okay? When the processor dozes off, there are various ways in hardware to make a processor doze off, but all of those would reduce battery or power consumption. So then what happens? What happens when I shake the phone? Well, the accelerometer chip is still awake, okay? It would do certain things at a lower frequency. So it would go like, oh, I just experienced, a change of force that is exceeding a certain threshold. Maybe the processor should know about this, okay? So then what it's going to do is it will raise an interrupt, okay? Raising an interrupt in hardware is basically just pulling a line from a high voltage to a low voltage. So the processor would actually detect that change. When the processor detects there's an interrupt, it would then wake up and go like, oh, okay, I need to go process that, okay? I need to get the data from the accelerometer chip and see if I need to display something on the screen. So that's interrupt driven. Now, how does that method of handling I/O devices have anything to do with what we are talking about here? That's the next question, okay? So let's just say that you have a phone and it is doing something already, okay? You're playing a video game, okay? So as you play a video game, the processor is quite busy doing all the rendering, it's busy, trying to figure out which character is interacting with each object in what way and so on and so forth. So it's already busy doing stuff, okay? When you press something on the screen, on the touch screen, okay, then it generates an interrupt. So what that interrupt is going to do is to say, hey, processor, hold on to whatever you were doing already. You need to process this now because we don't want to, we want that touch event to be processed as soon as possible. Okay? But the idea is when the processor is done processing the touch event, it needs to go back to do whatever it was doing before the touch event happens. Right? Because you don't want the processor to lose track of what it was doing just because you touched the screen or because you shook the phone, or something like that. So now the question is, what mechanism have we talked about that will provide that particular mechanism and go like, yeah, we know how to get back to where we were? The stack, particularly pushing a return address on the stack, do something. When you're done, pop the return address and use the return address to go back to what you were doing in the first place. Is that making any sense? Okay, so that means you can look at an interrupt as a function call that is done by hardware. It is not done in software in any way. It is done by hardware. Yes, go ahead.
So within like a computer and operating system, does that mean the operating system has its own stack?
Yes.
And then it allocates it gives us a bit of memory for all the programs stack?
Yes. So try to remember that question. Continue with what we just talked about, okay? And then we'll get back to your question because that's a very important question. So that means, with any type of chip, any processor that has I/O devices and it is interrupt driven, if you move the stack pointer, okay, right after you move the stack pointer, which is line 16 that I'm highlighting here, right after that moment, an interrupt can happen, okay? And that interrupt is going to use the very same location that you have just moved up to store the return address for the interrupt itself. Is that okay? and the interrupt happens, your processor goes process, whatever it needs to do, for the interrupt, and it will return, okay? But when it does return, the content of this location is already lost. It is no longer the content of local variable x, because it became the return address that the return address that the interrupt needs to store on the stack. Is that okay or not? Okay. So that's why on any type of architecture that supports input-output devices and interrupts, you don't want to change your stack pointer. You don't want to increment the stack pointer unless you're 100% sure whatever the stack pointer is currently pointing to is no longer needed. It can be clobbered right after you increment the stack pointer. Is that okay? So and to answer the other question, okay? So now the question is, who has a stack, okay? How many stacks do we have, when we run programs on a modern architecture? So the kernel has one, okay? The kernel is basically the first thread that comes into existence, when your program, when your whole operating system starts up. But basically every thread has a stack. So it's not every process, it is every thread, it has its own stack. A process can have multiple threads, but each thread in a process has its own stack. How many people understand what the word process means? A process is technically a program in execution. Is that okay? So when you look up, okay, so in Linux, I can show you how you can tell what programs are running. Okay, so let me switch to a command line. Okay. The most visual way to do it is top, okay, which is a command line program. It uses text to display, all this stuff, but each entry here is a process. It is a program in execution. So you can tell, okay, from the name or the path of the command, OBS is running. There's one instance of OBS running. The web content stuff, they're all coming from Firefox. Xorg is the GUI basic GUI engine that provides the graphical user interface. I got some IRQ stuff, okay? This is interrupt surface routine, okay? So this is actually handling some of the interrupts. XFWM4 is the XFCE4 window manager, and so on. So all of these are individual processes, but in each process, it can have multiple threads, okay? I'm not going to get into multi-threading programming here, but I'm just going to tell you one thing. Every thread in a multi-threaded process has its own stack, because every thread is capable of calling, returning, and do all the usual things that you do, when you write programs in a linear fashion. Okay? Yep.
Can multiple programs share the same thread?
No. So I think technically what you're asking is, can multiple processes, share the same thread? Yeah. And the answer is no. So the communication between threads and the communication between processes are entirely different. Threads share the same memory space, which means if you and I are different threads, we have our own stack, but we have access to the same global variables. We have the same heap. So if you do any type of dynamic allocation using the heap, in C++, using new and delete, right? In C, it is using malloc and free, but those things are common to us. So we can actually access the same global variable, the same heap space, and the same dynamically allocated object. So we have to kind of coordinate, because I don't want to modify something that you are in the process of modifying. So in the process of you working on something, you have to lock me out and say, I'm not done with it, okay? So even if the kernel says, okay, tag, you get to run, I have to respect that you are in the middle of doing something and not touch what you were working on. Okay, so that's inter-thread communication, which is a little bit tricky and it's really nasty when things go wrong. But between processes, they do not share a memory space. So each process cannot see the memory space of another process. So the only way they can communicate are through standard I/O, okay, STD I/O. So from your perspective, if you take C++, it'll be C in and C out. So the C out of one process becomes the cin of another process. That's one really kind of elementary way to have processes to talk to each other. Now, if you understand sockets, okay, server client model, that's another way, for more complicated communication between processes. But they do not share the same space, memory space. So communication between processes is a little bit more complex because of that. So did I answer the question? Okay. Yeah, so all of these are much more advanced topic than any class that we'll teach over here. They're probably concepts that you will understand in an operating system class as an upper division class in a 4-year university. So you'll get to these concepts again when you get to that class. Okay, so getting back to where we were, okay. So the idea is you don't want to, okay, let me just kind of bring up the two programs. So the idea is this is the right way of doing things. We do not change the stack pointer. This is the wrong way of doing things because I incremented the stack pointer even though whatever it was pointing to is still in use. Yep.
Would orientation of labels really matter or no?
Say that one more time.
Say if you did adder, like return address above X and then below that would be Y for the addresses, would that matter or no?
You mean exchanging the addresses of X and Y?
Well, just like starting from return address X1 plus and then below that Y1 plus and then below that Y. Would that matter or no?
The ordering of the label definition would not matter.
Okay.
Yeah. The assembler does resolve that automatically.
Does it?
Yep. If you have anything that is circular, the assembler should detect circular definitions. Even the ones that are not obvious, like if you define X to be Y1 plus and then you define Y to be X1 plus, the assembler would actually detect it as a circular reference and it would go like, nope, this is not resolvable. Yep.
On the left-hand side,
Mm-hmm.
on line 29, why was the stack pointer?
Well, why indeed? So let me go back to the browser, because in the browser, the spacer, which is basically an explanation of the concepts, would explain it. And I will point to exactly which one. It is because of this line. Oh. Okay. How's that? Okay. It's exactly because of this. Because we are the called subroutine is responsible to deallocate the return address. And that's part of the agreement. That's part of the deal between the caller and the called subroutine. Okay? Yep.
Now, would typically those values for X and Y still be on the stack, but when I point to them?
Aha. Okay, so let me answer that question. So to answer the question, okay, moment you have executed this instruction on an architecture that has interrupts, that thing that you just deallocated, which in this case is X first and then Y. So this is Y, okay? So technically speaking, right after this increment, that location can get clobbered by an interrupt already. So if no interrupt happens, yes, you still get the value of Y at that location, but you cannot count on it because interrupts are asynchronous events, which means the software, the program that you're running cannot anticipate when an interrupt can actually happen. So that means an interrupt can happen between any two instructions. So does that answer your question? Yep. Okay.
It saves it.
Yep. Mm-hmm.
This might be a question for later, but I'm curious. So if you have memory in the stack, like a local variable,
Mm-hmm.
you deallocate it, but don't actually wipe the memory out, and then an interrupt happens, and the next function gets access to the memory address. Couldn't it just kind of, I mean, assuming you didn't overwrite the return address something of the new function call,
Mm-hmm.
hop in there and say, oh, that function was working with this variable, and it's some sensitive data that's in RAM still. Is that a
Mm-hmm.
real concern for modern CPUs and stuff? You have to wipe up memory or like securely clear it out after you.
Okay, so to answer that question, I have to. The first thing is, if you're talking about a modern operating system like Linux, Mac OS 10, or Windows, post NT, then we are talking about a protected mode kernel, which means when interrupt happens, it's going to use the kernel stack and not the user stack. So as far as the user stack is concerned, it is not really affected by interrupts. But if you're looking at the kernel stack, that does get affected by interrupts. But even in the user space, your stack is still it's still used by signals, which is basically a way for processes to talk to each other. So you still cannot assume things that are below where the stack pointer points to will retain their value, because things can still happen and basically chew up that space. You can look at the stack pointer as a divider that says where the stack pointer points to and the locations above that, don't touch it. Nobody should touch it except for the thread that is running. But everything that is below where the stack pointer points to can be clobbered, can be used. It is just unused at the time. It is free for interrupts and other mechanisms to make use of the content below where the stack pointer points to. Is that okay? Or not? Question? Yep.
Could you draw a quick diagram?
A diagram.
Just like a stack picture.
Okay. So let's say we do have interrupts, okay? All right, so we'll take a picture of what the stack looks like at this point. So what the stack looks like, I'm going to use a slightly different notation where the square bracket indicates where the stack pointer is pointing to, okay? So at this point, we have the return address on the stack. We have X, which is allocated first on the stack. We have Y, which is allocated second on the stack. And that means, the stack pointer is pointing to Y. Is that okay? Does everybody understand this notation? Okay. So now, right after the increment instruction, what is happening right after, okay, is going to be something like this. The stack pointer is now pointing to X. Are we good? So let's say the toy processor architecture does support interrupts, okay? So if that happens, okay, I have to kind of comment here, interrupt happens. So when the interrupt happens, return address will still be there because it is above where the stack pointer points to, so it's safe. X is still okay because it is also above where the stack pointer points to. But in order for the interrupt to remember where to go back to, the interrupt, okay, interrupt return address is going to be overwriting what we knew as Y. So Y is gone at this point. And all of this can happen between the two increment instructions. So by the time we get to the second increment instruction, the content of Y can be gone already. And we have no idea when interrupt happens because it can happen between any two instructions. So that means, don't increment the stack pointer unless you know for sure whatever it was pointing to is no longer needed because you may not get it back. Yep.
So what if your stack ends up full and then there's an interrupt?
Then you get what we call a segmentation fault because it's going to force the stack pointer to point lower than the chunk of memory that is actually allocated, for the purpose of stack. And then your kernel is going to kick in and go like, you're not supposed to point to any location, earlier than this, or you're not supposed to. You can point to that, but you're not supposed to touch it. So then you will get a segmentation fault, which is basically a general description of you're trying to access a memory location that is not yet available to you. So depending on how the kernel is specified, some kernels can allocate additional space as you need more space. So it is possible that segmentation fault can cause the operating system to say, well, go ahead and extend your stack. So now that range of addresses is now available to this process. But typically, the size of the stack is predetermined, when the process starts. So you cannot, kind of dynamically allocate more memory when you run out. Question?
Yeah, I was gonna ask, what if you run out of memory in general?
There's not much you can do. I mean, you basically just so when you say run out of memory, you have to specify what type of memory you're running out of. So if you run out of RAM, it depends on when you run out. So do you run out when you do a malloc, or a new in C++, or are you running out when you try to start a new program, or are you running out, when your operating system is doing something? So that determines, the result of that. If you're in a C++ program and your new is running out of heap space, new just returns a null value to say there's no additional memory that we can allocate. So it returns a null pointer, and your program, okay, supposedly should catch that and say, we cannot allocate any additional memory, and then you typically will have to throw exceptions because most programs cannot proceed any further if you cannot allocate more using the new operator. So you basically will throw an exception, and then the exception will start to unfold the stack, and then all the way getting back to either a catch statement to catch the exception, or if no one is catching the exception, then it will just exit all the way out with an exception code. Question?
When you're saying the term kernel, what do you mean?
The kernel is the core part of an operating system. So when we say an operating system like Windows, okay, we are referring to a lot of different things, okay? So most people understand when we say Windows or Mac OS 10, they remember the part where you can use a mouse, click on something, you can double click on something, it starts, an application. That's really just the outermost layer of an operating system. It's the GUI, it's the graphical user interface. And then, kind of more or less parallel to that is the user interface or the command line interface in the form of a shell, okay? But that is also really just, the word shell means, guess what? It is on the outermost layer of an operating system at one point in time, okay? So the shell is really just a tool or a program that is capable of interacting with the end user using the keyboard, okay? But in the end, those components of an operating system would communicate with the inner more part of an operating system. So that would consist of your file systems, okay? The file system of an operating system determines when you plug in a thumb drive, okay? If you plug in a thumb drive that was formatted in Linux, would it work in Windows? Maybe, maybe not, okay? It depends on what file systems are supported by the operating system. If you plug in a new Wi-Fi USB dongle, okay, would your operating system know what to do with it? Well, that has to do with a driver of that particular device. So these things are not really exactly in the kernel, because these things can be added or deleted as you need, or as if you want to shrink an operating system, you can get rid of some of these that you think you don't need anymore. So file systems, device drivers, and many different kinds of surfaces, they're still not the core part of an operating system because they're basically just programs that are running that will do certain things. So when you move closer and closer, then you have a core part of an operating system that is responsible for memory allocation. It's responsible for how do I schedule threads and processes to make use of the processor. So that part that is core to the entire thing is called a kernel of an operating system. So the kernel typically, as a not so technical term, is referring to the innermost portion of an operating system that does not refer to file systems or devices. It is basically, no matter how you configure, no matter what hardware you plug in to your computer, that part is still there. Okay, any other questions? No questions? Okay, well, then we are, does everybody understand the stack versus interrupts, why it is not a good idea to increment the stack pointer? Okay, unless you're sure you don't need that stuff anymore. Okay, all right, so if there are no questions, then we will delete the code that is not going to work. Okay, so this is bad. This is a bad idea. Okay, don't increment the stack pointer unless you know you don't need it. This one is supposed to be a decrement because y is below x, so I have to stand corrected in this case. But between this time and this time, an interrupt could have happened and clobbered or overwritten the value of y. So by the time you get back to y, it doesn't have the same value anymore. Now, when you write programs in Linux, if let's say you're doing Raspberry Pi for an embedded system, you don't actually have to worry about this too much because your process is actually running in protected space or is in protected mode. So that means the kernel is the only one that has to deal with this. Okay, I think Signals would still use the stack space, so it would still be a bad idea. On the other hand, if you write programs on the Arduino, which has no operating system whatsoever, then your stack will be clobbered. So you have to be super careful when you play with or when you use the stack pointer on an architecture that has no protected mode, operating system. Is that okay? Yep.
If we wanted to use those values, we would have to put like labels or something else right in between the last word is stored. Well, it's different for each one, but stored B or A to B, and then before incremented D, right?
You just don't do it this way. You just don't do it this way. Basically, there's no way to recover once, if you do it this way, so you just don't do it. And you use the other way. So if you look at this code here, after the two initial decrement D stays the same until we get to here, which means, okay, so let me show you the code in between, because this is a very important concept. Okay, this is the last decrement D. So between line 6 and the first increment D, interrupt can happen and whatnot, but we won't lose anything. Because everything that this particular invocation of F needs is either pointed to by the stack pointer or above where the stack pointer points to. So interrupt can happen and use and chew up and corrupt and overwrite the locations that are below where the stack pointer points to, but it would be of no concern to me because as far as I'm concerned, everything that I need are either pointed to or above where the stack pointer points to. Is that okay? Right? So this is the proper way of doing things, is do not increase the stack pointer just because you need to access something that is on the stack. You only increment the stack pointer when you don't need that thing on the stack anymore. Are we good so far? Yep.
So if an interrupt an interrupt can come in and change all of the registers, it wouldn't matter.
Okay, so that's a good question. The question is, an interrupt can come in and change. What can it change? The answer is it's not supposed to. So if it does need any of the registers, it has to save and restore the register. So the implementation of interrupts, it would require quite a bit more instructions because I would need to have basically an instruction, one microcode to handle the entry point of an interrupt, which is basically to save the registers on the stack, blah blah blah. And then when the interrupt is concluded, then it has to restore the registers. Yep. So it is as if the interrupt. So to your code, it is as if the interrupt never happened. Yep. Except for things that are below where the stack pointer points to, could have changed. But that should be of no concern to you because all the stuff that you need should be at or above where the stack pointer points to.
So you write code to deal with interrupts?
Yes. So the code that deals with interrupts, they're generally called ISRs, for interrupt service routines. They are, for the most part, they look just like regular functions, okay, regular subroutines, except for two things. One is, at the entry point of those things, you save all the registers that you're going to modify. And at the exit point, you restore all the things that you have modified but saved earlier. So to the code that it was interrupting, it is as if nothing happened. And depending on the architecture, when you return, you also need to re-enable interrupts because when an interrupt happens and you're trying to handle that interrupt, most architectures will turn off interrupts so they cannot stack interrupts.
Yeah.
But I said most.
Right.
There are certain architectures don't do that allows one interrupt to stack on top of the other one. And it's nice in a way, but also really messy to deal with in many other ways. Yeah. So when you look at the Intel architecture, it automatically disables interrupt when you're in the process of handling one interrupt. Any other questions related to interrupts? because it's a very important concept, even though most of us will never see it. Okay, you'll only see it when you need to write driver code. So let's say you're working with you make a new USB device, okay, and you plug into the USB bus. Well, USB devices may not need to deal with interrupts directly because the USB hub driver itself is the one that needs to deal with interrupts. How many people think that in order to deal with interrupts, you need to learn assembly language programming for that particular architecture? Okay, that's not entirely true. GCC is capable of generating code for ISRs or interrupt surface routines if you just specify the keyword interrupt before the declaration of the subroutine itself. So we'll attach additional code to save all the registers at the beginning, at the entry point, and it will also attach additional code to restore the value of registers at the return point. It will also it will automatically reactivate interrupt and do all kinds of things that you need to do. So you don't even need assembly language programming to handle interrupts. Yep.
Wouldn't it have to be specific to the CPU's architecture, though?
It is specific. So it depends on what you're handling. So so what do you think happens when you're inside an ISR? Okay, interrupt surface routine.
You mean like when it's called, or
When the interrupt happens. So when interrupt happens, the ISR eventually gets control. So what do you do inside an ISR? So let's say it's an ISR or interrupt surface routine that is corresponding to the touch screen mechanism of a phone. So what do you do?
Save the stack pointer.
Right, obviously take all the.
That's automatic.
Right.
That's already done.
Okay.
So what is the job, the main job of an interrupt surface routine for the touch screen on a cell phone?
to start next line
Accepting
of code, like to well that's the thing. That's the interrupt's job. It accepts the input. I'm guessing it starts wherever, like whatever command it's supposed to do. Say if you touch a screen, it's supposed to start whatever subroutine.
So you ask it will ask the touch screen chipset, right? And say, okay, what was the event?
Yeah.
What is the X value? What is the Y value? What is the capacitance that you have measured? Because all of that stuff is done by the chipset. So by the time the main CPU asks the chipset, it would get the answers from the chipset. Okay, what is the coordinate and how big of a press is that by capacitance? So once you get that information, what do? Okay, now that you know that you got an event at location 2016X, 3600 Y, and the capacitance measured is a certain number of nanofarad. So what do you do next?
It run code and then it goes back to wherever it stopped, halted, or where the last pointer was saved.
Okay, but somehow the rest of Android needs to know that touch event, right? So the interrupt surface routine will have to put that event into a small object and put it into a queue so that your GUI will eventually go to that particular entry, pick up that object as an event, and then your Android operating system or Mac or iOS will then interpret that event and go like, okay, which application are we running on the foreground? That one. Okay. And then it will relay that event to the application and say, hey, Firefox or Chrome, you just got a touch event of this magnitude at that location. So it will put that event into the event queue of the app, and then the app will then pick up the event, and then depending on how the app is programmed, it may not even have a handler for a touch event during that time. So it would just go like nothing to do. Or if you have an event handler for touch, that at that portion of your application, then it will go to the correct event handler to execute whatever code that is associated with that particular event. Yeah, it's a long journey for that event to get surfaced. Yep.
So basically, when an interrupt happens, it gets packaged and then sent onto a conveyor belt.
Yeah, exactly. Exactly.
Yeah.
Yeah, a conveyor belt is a queue because it's a first in, first out. Yep. Yep.
Well, we need to know this for discrete structures because I know that you're the only one who's teaching it.
You don't need that for discrete structure, but you do need to understand that general concept of an event queue and whatnot if you want to get into any type of programming that has user interface. It can be JavaScript programming on the client side, okay? It's event driven. It can be Android programming, it's event driven. It can be iOS programming, it's event driven. So basically, most modern apps that has any type of user interface is event driven. And that's basically what's going on.
So everything.
Yeah, just about everything. Yep.
You wanna do cool stuff, but
Well, I mean, these concepts, they all kind of add up, to become important. Yep. Okay. So any other questions? If anyone is continuing at Sac State, CSU Sacramento, I believe they have a system programming class, where they will re-explore some of the items that we talked about today. All right. Are we good so far? Yeah. So we have concluded, a lot of things already because we talked about the calling and returning mechanism. We talked about, how to push arguments on the stack and then access those arguments as parameters from the perspective of the called subroutine. We talked about how to return a value. That was one of the shortest topic ever, right? Whatever you need to return, put it into register A. We're done, okay? We talked about local variables. We just talked about local variables. And in the process, we also talk about how to access local variables, and it also works on parameters because parameters are also on the stack, and you can use the same method to label the parameters that you need to access from the perspective of a called subroutine. Yes?
So from that way, you can just think about parameters as just local variables that are declared before the function starts. Right?
Yes, absolutely. Yep, that's basically what they are. All right, so let's move on to the next question, okay? Because I just want to kind of go through these questions one by one to make sure that we have the knowledge, okay, to do all of these. The questions themselves, it would actually talk about that too, okay? So, like in this slide here, okay, we have the C code, and then there's the assembly code, which is implemented slightly differently. So you need to make sure that this code, you need to understand why this code also works, even though it does look different. Okay, and let's see. This one is asking. Occasionally, we need to refer to the address of a local variable. So we have a function like this, which is a swap subroutine. Okay. Now this one is not a swap subroutine. Okay. So look at this code. Look at function f. Okay. If you look at function f, we have two local variables, x and y. We know how to deal with x and y, right? So x equals 5, y equals to 20, not a problem. We know how to do that. But now the next question is, if I have a function, a different function g, that requires the pointer to a particular uint8 and the pointer to another uint8, how do I pass the addresses along? You have to push those on the stack, okay? So that becomes kind of, so if you read the code, it's going to explain how it is done, okay? So this so-called lab is going to take a little bit longer than the usual one, because it actually contains instruction along with, what you need to do. So look at it as kind of like an interactive instruction where you're learning something, but you're also practicing at the same time, okay? So we can go back to our program, okay, and ask, well, how do we deal with this particular function f, now that we have this additional line of we want to call function g with the address of x and the address of y. Okay, so this is what we're going to do now. So we get to the end of the previous program, which is right here, and then we ask that question. How do we push the address of y on a stack? How do we compute the address of y? How do we get to just this expression here? Well, it's not too hard, right? Because we have that already. We did that before. So we can do exactly just that. Okay, so we can say LDI by add BD. So at this point, B is the address of Y. We have to push it on the stack. Okay, pushing something on the stack means we decrement D, we allocate one space on the stack, and then we store to whatever D is pointing to, and then specify the value of that whatever we want to store. So at this point, we have pushed the address of Y on the stack successfully, not a problem. But the next one is going to be tricky, because now we need to compute the address of X. Okay? So in order to understand why it is a little bit tricky now, let's see what is on the stack from the perspective of this particular called subroutine. What is on the stack is, as usual, the return address being the highest item. The next one down is X. The next one down is Y. But guess what? The stack pointer is pointing to the first argument that we have just pushed on the stack, which is the address of Y. Is that okay? So when we need to compute the address of X, X is no longer just 1 byte away from where the stack pointer is pointing to. It is now 2 bytes away. Does everybody understand why X is now 2 bytes away from where the stack pointer points to instead of just 1? Because we just pushed something on the stack. So that means now you have to keep track, because as the developer or the programmer of this program, you have to now keep track of that and go like, oh, in order to compute the address of X, we can do something like what we did before, like that, okay? But you have to remember that you have to account for that 1 additional byte that you have used to push the argument, okay? So we'll say it's because of address of Y that is pushed on the stack.
That's a valid statement.
Hmm?
1 plus, that's a valid statement.
Yeah.
LDI.
Yeah, perfectly okay. Because this is in postfix notation, all that means is I'm computing the sum between X and 1. X as a label is 1 already. So 1 and 1, the sum is 2. So X1 plus would evaluate to 2. Okay? And don't forget, you still have to add a D to B, because otherwise it's just 2. 2 is not the address of X. 2 after where the stack pointer points to is the address of X. So let me just pause and make sure everybody understood that particular statement. Is that okay? Let me repeat that statement, and if you have any questions, you'll let me know. B, on line 31, B does not have the address of X. It has the displacement to X from where register D is pointing to, which is a constant of 2. But 2 is not the address. It is just an offset. So that's why we need line 32 to add the value of the stack pointer to register B in order for B to be the actual address of X. Yep.
So is that why you always want to, whenever you allocate like label, or you have labels, you always want to use like what's before it's pointing to, so
Yep.
it's always consistent?
So it's consistent, and if you need to add additional local variable, the amount of code you need to change would not be that much. But that part is up to you. So now that B, okay, so at this point, okay, B is now the address of Y, which means now we can push it, which is decrement D, stdb, okay? So now we have the address of Y pushed first because it's the second parameter, and then we also have the address of X pushed second because it's the first argument. Now we can do the call. So in order to do the call, we decrement D first, and then we do a LDI, and then we can use any of the registers, A, B, or C. So we can use A in this case, 1, 5 plus, and then we do a stda to save the return address, and then we have a JMPI to the subroutine that we're calling. In this case, it is G. When G returns to line 39, what do we need to do? What is the responsibility of the caller in a subroutine? To allocate the arguments, right? So we have the address of X and the address of Y pushed on the stack at this point. The return address is done already because the subroutine is responsible to deallocate the return address. So that means at this time, okay, so let's check out what the stack would look like at this point, okay? So we have my own return address. We have local variable X, local variable Y, and then because I passed those along to the subroutine X, we will have the address of Y pushed first, and then the address of X pushed second. This is what the stack looks like at this point. The stack pointer is pointing back to the first argument. Hi, Rodney. So let me finish this sentence and then we'll do that, okay? So this is what the stack looks like, okay? But in order to go back to where the stack pointer was pointing to, we need to increment the stack pointer twice so that it goes back and point to y, because that's where the stack pointer is supposed to be at when the stack is balanced. So now we want this in the picture. To get to this, we just have to increment the stack pointer twice to deallocate the two arguments that we push on stack because of the call to G. Yep.
Back on line 31, why wasn't that 2 plus if it's 2 away? Is it because x?
It is only 1 plus because this decrement D is what kind of messed things up a little bit. So we need to use this one, on line 31 to account for the decrement D on line 28. And that's why it's just 1, because we just got one additional thing pushed on stack. So it changes the displacement between the stack pointer, where the stack pointer points to, and the items that I have already placed on the stack. Okay, so I'm going to turn the class over to Rodney a little bit because he is going to tell you guys more about the HP Enterprise internship thing. So, Rodney, you want a mic?
No, I'm good. Everybody, my name is Rodney, and I'm here to talk about the Hewlett Packard Enterprise internship. Yeah. So, Hewlett Packard, are you guys familiar with it?
Yeah.
Okay, you guys know about it? Okay, cool. All right. Well, I haven't seen nobody yet. So do I need to talk about it?
No, go ahead.
Please talk about it.
Okay, yeah. So last year, Hewlett Packard, we established an internship with their company for a summer internship. It started last year at this time. We receive student applications. I meet with the students, get everything worked out, and then I forward all the students so I recommend students over there to Hewlett Packard. Hewlett Packard brings in, and then Hewlett Packard will invite the students that they want to interview for an internship. Last summer, we had 4 students take part in the summer internship. It's full-time, benefits, paid internship at Hewlett Packard right here in Roseville. 3 of our students has transferred on, and 1 of the students is still a student here. So we're in the process of receiving it's still open, and then they're going to offer the same thing for next summer. So this is going to be summer of 2020. And then, as I was telling last week, most big companies maybe only have 1 or 2 positions. Well, Hewlett Packard had 4 of our students just for American River College. So when you guys go online and look at the links, the purple briefcase, that's for all students in the whole district. The internship that I established here, and this internship, is just for students here at American River College. So you're not competing with 5,000 students. It's just a few students here that attend ARC, and that's another outstanding thing about it. And it worked out so well last semester. They're going to bring it back again for next summer. Some of you students went when they were on campus a couple of weeks ago. Yeah, so that's the gentleman who's going to be running point on the community college component. Do not go online because they do not have a community college internship program. They have a high school component and they have a 4-year component. But this particular one here is specifically for our students here at American River College. So no information you're going to see will be on the HPE's website. So you got to come through me, and then everything is going to be sent over to Jeremy at Hewlett Packard. Any questions? No? Anybody want a flyer? Cool. So, and how many? What you guys will be doing on the internship? That I have no idea because there's different teams. So every student that they bring in, they'll put on a team. So you'll work on teams and all that. So last year, so that you guys know, they had, this is company wide. So they had 80 teams of 4 interns. So this is company wide. So, anything else? No? You guys good? Okay, cool. So last year they had at the end of the internship they had a hackathon. So they had 80 teams with 4 people on it. I mean, this is company wide. They're a large company. So our students here at ARC got second place.
And that's competing against teams
That's
from
competing
4-year
against
universities.
All the 4-year institutions, not the high school teams. All the 4-year institutions, and that's all the 4 years. I'm talking about Colorado, Harvard, SC. And that's company wide. Out of all the 4-year schools, ARC's team got second place. And then when I talked, so yes, and then they said that they almost won. They almost got first place. So.
That's why they're back this semester, right?
Yes, and that's why we're back this semester. Excuse me?
We'll win this time.
Yeah, so that's why we're back this semester. So I personally think when we engage in this conversation of having the internship program with community college students, they was like, okay, cool, we'll do it. Whatever. We'll make you happy. I honestly think that. So then when we started getting the applications in, it went from 1 student to 2 students to 3 students to 4. Those 4 students got second place out of company wide, and that's pretty good. I think that's why they want our students to return too. Yeah. And actually, I know you'll probably make more money in the summer than you'll probably make all year. Pays very well.
Probably better than me.
Pays very well. So you can't always look at the internship for the pay, but I can honestly say this one is pretty good. It's worth applying for it. Excuse me?
It's helpful.
It's very helpful, and it pays very well. And it pays like almost, it pays very well. And let's just say that, I'm not going to tell you
It pays
how much,
almost
but
too much.
it does, it pays very well. So so a company as big as HP, they can afford it. So that's why I say if you get an opportunity, and the internship with the students last year, it started the end of the semester here, and then it ran through whenever their school started next year. So it went from May 18th till 2 of them went to Davis, so September, and then the other one went to Santa Cruz, so September. So it runs through the whole entire semester. So whenever the end of your